Okay, so good afternoon, everyone. Everyone's here already, I think. Yeah, recording has started. Okay, so we just have one small thing left to finish, and then after that we will finish the entire syllabus, and then we do the final tutorial, which is tutorial 10, and then yeah, and then that's about it already, right? So we are finishing the last few things. So this is the final lecture of today, right? So this is our season finale, right? We just need to do the tutorial, and then yeah, if you have any question, you can ask it here. Otherwise, we will most likely to be finishing early for today, okay? And then next week, from here on, you guys will start studying for the exams already. So yeah, so let's finish off the space-time diagram. So this was something that we were supposed to finish in Monday's class. Just a few things to talk about, right? So we were talking about light cone, and light cone in a space-time diagram. So space-time diagram is talking about, well, how events happen and influence each other, because everything, this one is nothing special, nothing complicated like Lorentz transformation and things like that, although you can represent a Lorentz transformation using a space-time diagram, where the space-time diagram angle change. So we don't worry about that. We will not do this here. I don't find it very helpful actually, but sometimes the YouTube video, some of them Zuri and I have shared, right? The videos they got discussed about how you use space-time diagram to represent the Lorentz transformation, and the frame S prime to S is like the changing of the axis. But yeah, this is something that we won't be doing much today. Here I just want to discuss the consequences of the speed of light being our speed limit of the universe. So nothing can travel faster than light, right? So absolutely nothing. So that means any information that you want to transmit from one place to another, at most it can travel at equal to the speed of light. Other types of information will be slower. So that will define our concept of the light cone. Okay, so light cone, we say that we talk about the causal connection, right? So what we left off on last class was the idea of the causal connection. So causal connection are for things that lie inside each other's light cone. So causal connection. Okay, so we have an event P. So the first point is a future. How does an event affect something in the future? So an event P can it influence another future. So we are talking about something happen in front in time, right? Event Q only if Q lies in the light cone of P. So an event P means something happening. Okay, so when something happening, what are the consequences? So what are the consequences? So the consequences will be happening inside here. Okay, so it will be something within the light cone, right? So that means there's two possibilities. If Q is inside this light cone, then things that happen in P might affect Q. Okay, but if Q is outside this light cone, then things in whatever happens in P, it will not affect this event Q. Okay, so event, remember, it's not just about position, but it's about position and time. So Q is this position at this time. So whatever happens in P will not affect Q2, but it will affect Q1 because it is possible to send information from P to Q. Okay, so we say that Q1 is causally connected to P, but Q2 is disconnected, so it's causally disconnected. From P. So nothing can travel between P to Q. Okay, so that is how event P can influence future events. And we can also talk about the past of P. So what are the things that can influence the event P? So things that are happening behind, right? So everything will cause to influence the outcome of P. So everything will be behind P. So now we can talk about a past event. So a past event, let's talk about event P first. So an event P was influenced by a past event Q. Actually we say can be influenced, right? Because maybe not, maybe the influence is not direct and things like that, because we're talking very general. So it might be possible or not possible. Past event R only if R lies in the light cone of P. Okay, so it's very straightforward. We draw the light cone again, and it's the similar thing but in the past. Okay, so in the past, so let's draw the light cone. Okay, so this is our light cone here, right? So these are all the things that can be related to P. So a previous event, so let's say R1 is here and another event R2 is here. So if R1 is inside the light cone, so whatever happens to R1 might be affected by P, right? So when something happens here, P might know about it. Okay, if something happens to R, then P will know. So R1 is causally connected to P, but R2 is causally disconnected. It is outside the light cone. So if you're outside the light cone, whatever happens is R is too far away, right? If it's too far away, then the light doesn't have enough time to travel towards between R and P. So you need to travel faster than light. Nothing can travel faster than light. So nothing can communicate between R2 and P. So it's causally disconnected to P. Okay, so these are the basic concepts of the light cone. Okay, so yeah. Will you learn special relativity in future courses? Your modern physics will have some implication, but you won't learn it directly. You will learn there's a future course for general relativity, so definitely you will learn it. And then of course in that course we will recap special relativity briefly, and then also besides that I think probably no more, unless for higher level courses like graduate school or things like that. For grad school, right, special relativity is important if you want to learn things like quantum field theory, condensed matter physics, and those kind of things. Then you do need special relativity. So yeah, so you won't learn it in the immediate future, but a bit further down the road. Okay, yeah. Okay, so I guess if you are still interested in special relativity, what you can do meanwhile is to read up a bit more about it. Well, because you guys will be learning other interesting things as well, quantum mechanics being the main part, right? So interestingly, special relativity, even though it's older, right, is not being directly used for your next few courses. Ironically, quantum mechanics is more relevant because it's being used in all the other specialties of physics. So yeah. Okay. Yeah, so one last thing to do is to talk about the star Betelgeuse, right? So let's call this topic is Betelgeuse. Okay. Okay, so if you see the news, right, last year, I think around January of last year, like exactly 1 year ago, around this time, early last year, people were seeing news about Betelgeuse, that suddenly Betelgeuse, the star, become darker, right? And people are wondering what's going on, and maybe people are scared that Betelgeuse might one day explode. So it is very likely to explode relatively soon compared to other stars, because this is a star that is very old and is going to die very soon, and the star of Betelgeuse mass will probably die by a supernova explosion. So we might expect maybe we get to see Betelgeuse explode. If it does explode, right, it is going to be very, very bright because it is relatively close to Earth, and we might see it very obviously at night. So yeah, so let me explain why are we talking about this in terms of space-time diagram. We want to talk about the light from if Betelgeuse explode, right, the light from the explosion, all the explosion light it will have to come to Earth, but these are light, so it has to travel in the speed of light. So let us talk about this. The Betelgeuse is an very old, okay, red giant star. It's a star that is 642.5 light years from Earth. Okay, so 1 light years is 6.079 times 10 to the 18 meters. Okay, so this is very, very far away from the Earth. So by the way, right, if you read the Hitchhiker's Guide to the Galaxy, Betelgeuse is the home system for one of the characters, Ford Perfect, I think, right? So if Betelgeuse explode, right, the light from the explosion will take 642 years to reach Earth. So even if it exploded now, we would not notice it until 600 years into the future. If we see it exploding now, right, if we see the explosion now, that means it has exploded 600 years ago. So this is because of the space-time diagram. So we can draw everything on the space-time diagram, right? So our space-time diagram is our position axis is here, our time axis is here, right? And then let's say our Betelgeuse, the world line of Betelgeuse is here. So Betelgeuse is not moving relative to our galaxy, so we can take our galaxy as a reference frame, right? So relative to the galaxy, it is more or less in a fixed position, right? The distance from the center of the galaxy. So this is the world line. This is the world line of Betelgeuse. And Earth is also about the more or less the same distance from the center of the galaxy all the time, so it's still another straight line. So this is the world line of our solar system. Of Earth. So we are relatively not moving, okay? And then the distance between these two is 642 light years. So in SI units, my distance is 6.079 times 10 to the 18 meters. Okay, so if the event P, so the event is something happening at some position at some time. So let's say the event is that explosion. Okay, so the event is Betelgeuse explodes. Then the time taken for the explosion, well, if it explodes now, it will not affect our Earth today, right? But it will affect us in some future time in this light cone. Okay, so this is the light cone. Okay, so the light from the explosion will only reach the Earth at this time. So at this time, that is, according to this frame, it is this amount after the explosion. Okay, so from here we see that because the light from the explosion is traveling at the speed of light, correct? So the speed of light is just the change in position over the change in time is equal to c. So when will we see the explosion? It's just delta x over c. So the distance is 6.079 times 10 to the power 18, and then the speed of light is 3 times 10 to the power 8, so it is going to be 642.5 years. Okay, so that is what happens. So light from the explosion takes 642.5 years to reach Earth's position. So we're talking about events influencing each other event, right? Let's say the explosion is so big that the explosion can actually destroy the Earth. So if that happens, right, if the explosion happens now, it will not destroy the Earth here. So this event cannot affect the Earth today, right? So it only takes time for light to travel. So even if the explosion destroys the Earth, then it can only affect the Earth at 642 years into the future. So that is the what it means by causal connection, right? To use a more dramatic purposes. Okay, so yeah, so this is what we say. So it takes this much years to reach Earth's position. So whatever happens to Betelgeuse right now, it will not affect Earth until 642.5 years later. Okay, so that is the meaning of the space-time diagram, right? So I believe this is a pretty obvious explanation, knowing that signal can travel in a finite velocity, so therefore whatever you want to affect something, to communicate, to transmit signal, or to exert a force or anything, right, it can only happen within the constraints of the speed of light. So everything must be happening inside the light cone. So that is the main concept of the space-time diagram and light cone that I want to convey to you at least at this final last few hours of this course. This stuff is not examinable, but related to the question whether you learn it in the future, right? The concept of causal connection will be important when you learn quantum field theory later, because when you want to calculate quantum field theory is like quantum mechanics plus special relativity. So if you want to consider like one particle affect another particle, right, then you want to calculate the quantum correlations. So then by that time you will learn a lot of math already, so you learn how to calculate correlation functions and things like that. But the correlation function has a constraint, right? It has a constraint that the 2-point correlation function must be within each other's light cone. So if it's outside the light cone, then the correlation function is 0. Then yeah, so you guys don't know what I'm talking about now, but I'm telling you this now because it will affect your your understanding of correlation function into the future. So I guess you can keep these notes until the next time you come across this concept again. Okay, so yeah, for things like quantum field theory and things like that, and even electromagnetism, if you want to calculate radiation itself, light, right? So the potential energy function must have some time component to it. So we call this the advanced potential and the retarded potential, and then from there there's advanced Green function, retarded Green function. So all this again you will come across it in the future. You don't know what I'm talking about yet, but it will be this kind of stuff will be quite important. Okay, so that's it, right? Okay, so lots of things here. Let me clear my notes and then I read your question. Hang on, I'll be back. Quantum is applicable. Yes, that's true. Yeah, because quantum mechanics is being used in a lot of places. So quantum finance is one of the things. Correct, that is true. Yes. So that is the consequence of the space-time diagram, right? So all the light that we are observing on Earth, right, came from Betelgeuse 642 years ago. So another consequence of looking at things into space, right, because things are so far away, the light that left the star actually originated in hundreds and thousands of years ago. Then only it reaches the Earth, then we see the image, right? So we see the image very late, and seeing stars in that sense is like looking back into the past. So that is an interesting way to look at space. Yeah. Correct. So that's what I was saying now. So if we see it explode today, right? If to our position, if we see the explosion, that means it has already exploded 600 years ago. Yeah, so it has already happened in the past. It will lose energy during transmission. Radiation will arrive. Yeah, so assuming the radiation of so I'm taking the simple case here because explosion has a light, right? So it's like something explodes or something very bright. So that is a light, electromagnetic radiation. then this electromagnetic radiation is light. It travels at the speed of light, so it will come to Earth at the speed of light. So other particles like the neutrino from an explosion, okay, so explosion will generate all kinds of particles as well, like all these neutrino, mesons and pions, right? But some of those are unstable, but the neutrino are stable enough to travel all the way to Earth. But the neutrino from the explosion, neutrino has a mass, so it cannot travel at the speed of light. So it will arrive at the Earth a bit later. So there's a time lag. Then yes, then these are the things that will happen if you encounter all kinds of particles. So yeah, correct. For massive particles, it will be later. So the radiation loss, yeah, in general, right? Because if you assume radiation travel, this is something you will learn in the next course, is that if you emit the energy from a radiation, right, because it's spread out it's spread out over a large volume, so the energy is constant, but the energy per volume will be decreasing because the energy is dissipated over a large area, right? So by this time, the surface area of this light emission will be very large, so the concentration of the energy, the flux will decrease, right? But the total energy is conserved because it's everywhere in all directions. But what we measure is this part only, and that will decrease by the area. Yeah, so it's basically after it explodes, is everything the same thing for light. So you can take an object to block the light, block the view and things like that. Then yeah, so everything is just the normal ordinary blocking of light and stuff. Yeah. Okay. So this is page 2. Then we're done with the syllabus, right? So that's all the things. The final topic of special relativity. Okay, so actually everything you learn in your first 2 years, right? In your first year especially, first 2 semesters, mechanics, thermodynamics, electromagnetism, modern physics, you learn everything first, and then in your future years you will learn it again in a more deeper sense, in a more rigorous and complicated scenarios. So yeah, so mechanics stuff you will learn it again in year 2, but more advanced methods like Lagrangians, Hamiltonians and things like that. Okay, so it's not the end of like talking about mechanics, so you will encounter it all the time. And basically physics is like learning and relearning the same thing over and over again, but in more and more sophisticated methods. Dark matter, so dark matter, no, at the moment the nature of dark matter is it doesn't interact with light, right? We call it dark matter because it doesn't emit light, but it also doesn't absorb light. So if there's an explosion, then so far as we know, the dark matter doesn't absorb light from other sources. It doesn't emit light, that's why we call it dark, but it also doesn't absorb. So can it reflect? Also no. Yeah, because if it can, right, then we would have observed that already. Then we would have solved the dark matter problem. So that is why dark matter problem is a problem. We can't see it, it can't reflect light, it can't absorb light, it can't transmit light or emit light. So we cannot see it, we cannot measure anything about it. And when it comes to astronomy, right, everything is dependent on the electromagnetic radiation coming to Earth. So if it doesn't interact with electromagnetic radiation, it's very difficult to do anything. Unless we talk about yeah, it doesn't absorb or emit light. Yeah, it doesn't do anything. Yeah, we haven't seen it because there's nothing related to it hasn't affected light in any sense, so that's why we can't detect it. What we do know, the reason why we suggest the possibility of dark matter is because of the gravity. I shown you before, right, in the very first class. And then it seems to affect the total mass of the galaxy, but otherwise it only has some gravitational component, but no electromagnetic interactions with other objects, and we don't know why. Hopefully. Right now, that's why gravitational wave is a big advance in astronomy, because right now we can observe things in space, not just depends on light anymore, but gravitational waves. So if dark matter is tasty, then it would be a very good resource, right? We can solve world hunger if we can find it and eat it. Okay, so that's about it for this stuff. So let's talk about the tutorial. And as you can see, right, the tutorial, for most of the tutorial, the key step is to identify the variables. Once we identify the variables, the rest, the calculation itself is very straightforward, then it becomes very fast. So we'll probably finish everything in the first hour, maybe. I don't know. Well, it depends. Let's see. So let's start with question 1. We have a negative pion. Am I recording? Test. Is it recording here? Yes. Actually, that's a good point, because dark matter is supposed to be in the all over the galaxy, so it's around us. If it exists, we are probably breathing it in right now. It's passing through our bodies right now. So question 1, negative pion is an unstable particle and this is the average lifetime. So we just take this as the time it exists, and then we measure this. If this is the time, if we measure this in the rest frame of the pion, that tells us that this number is a proper time. Okay, so the pion is made to travel at a very high speed. Let me write this down first. So 2.60 times 10 to the 8 seconds. This is the proper time. Right, it's measured in the rest frame of the pion. And then if the pion is made to travel at a high speed relative to a laboratory, average lifetime measured by the lab is this much. So that has a time dilation. And use this, calculate the speed of the pion. Obviously, it means relative to the laboratory. So we want to calculate the gamma factor, the Lorentz factor, using this method. Okay, so lab measures. The delta t is 4.20 times 10 to the 7 seconds. So we got the time dilation, right? So this is measured by lab, is not the proper time. It will be the dilation of the proper time of delta t0. Okay, so from here we want to determine the speed relative to the lab. So I want to find u, right? So gamma t0 is equals to the square root of 1 minus u squared over t squared. So we just need to perform this calculation, right? So once we got identify the parameters correctly, then the rest is very straightforward, right? So delta t, right? So in other words, this is c squared. U squared over c squared is square both sides and then take 1 minus over, so I got t0 over delta t. So you put in the numbers, you will find that u is 0.998 c. Okay, so just like that, very straightforward. Okay, so the next part is, what is the distance traveled by the pion during this lifetime? So we know the time taken, we know how fast a particle traveled relative to the lab, so we just need to take u is equals to u delta t times u, right? So it's just 126 meters. Okay, so just like that. A lot of interesting implications there. Yeah, this one can be something that can be written into a story like a Hitchhiker's Guide, you know, something quite strange and funny. And I remember in the Hitchhiker's Guide to the Galaxy, like, there is a pig at the end of the universe who is alive and he's willing to give his leg for you to eat. I remember something weird like that. Yeah, so let's go to question 2. So question 2 is apparently it's a Star Wars question. Coruscant, right? So a spacecraft flies past the planet Coruscant at a speed 0.6 c. So the relative speed between the spacecraft and Coruscant is 0.6 c. So this is the relative speed. A scientist on Coruscant measures the length of the moving spacecraft to be 74 meters. So this is not the proper length, right? So it's 74.0 meters. Then the spacecraft lands on Coruscant and then measures the length of the spacecraft. So after the spacecraft lands, right? After the spacecraft lands, then it becomes the proper length. So now they're in the same frame together, and the scientists measure the length of the spacecraft again. The scientists will get what was it? Yeah, we want to determine what is the proper length. Okay, so we want to calculate this, right? So this is the just using the length contraction formula. You know, reading this question suddenly made me think, right? In Star Wars, all the scientists are bad guys, and because only the Imperial or the Empire have scientists, and the rebels, almost none of them are scientists. But yeah, I'll think about this later. Let's focus on this first. We want to find L, right? So gamma, 1 over gamma is u square over c square, and then times L0. So remember, the Lorentz factor formula is 1 over the square root, right? Not the square root itself. Usually people will make this mistake. They remember wrongly. Gamma, the square root, the square root is downstairs in the gamma. So 1 over gamma means the square root is up. So I want to find L0. So L0 is just L over 1 minus u square over c square. So you just take 74 meters, and then 1 minus 0.6 c over c square. So yeah, so usually they will cancel the c for you, right? So usually they give you in terms of c, so it's easier to calculate. Just need to cancel off the c, and then the length that you get is 92.5 meters. Okay, so very simple, right? Yeah, let's go to the next question. Question 3 is slightly more involved, well, just because it has 3 parts. So let's see. Unstable particle, could be a pion again, right? It's created in the upper atmosphere from a cosmic ray and travels down towards the Earth at very high speed relative to the Earth. So a scientist on the Earth measures the particle is created at this height, right? So that means this is the length traveled by the particle in the Earth frame. So as measured by the scientists, how much time does it take for the particle to travel to this part of the Earth? So the first part is just using normal kinematics calculation, right? Because everything is talking about the same frame. So the relative speed of the particle relative to Earth is 99540 c, and then for part A is well, the distance traveled is just going to be u delta t, right? So from here we can get the time interval of this process. So it's the length traveled by the particle divided by the speed of the particle. Both of these are measured by the frame of the scientist on Earth, so we can calculate them together. So the distance is 45 kilometers, so 45,000 meters, and then u is 0.99540 c, so times 3 times 10 to the 8, and then the time is 1.507 times 10 to the minus 4 seconds. So this is the time taken by the as measured by the Earth. Okay, so for the next part, using length contraction formula, what is the distance traveled by the particle according to the particle itself? Okay, so yeah, so that means, right, we are talking about the Earth here. So so the Earth, and then the particle is traveling down. So the distance traveled by the particle, right? So the distance, the starting point of the particle and the ending point of the particle is here. So this length is the proper length in the Earth frame. Okay, so this length is the proper length for Earth. So Earth has a proper length. So therefore, and the particle is traveling relative to this length. So particle will have the length contraction value. Measurement. So if you measure length, it will be contracted. Okay. So what is the length measured by the particle? It's just going to be L is L0 over gamma. So it's 1 minus u squared over c squared, right? So times the proper length. So the speed that the particle travel is 0.9954 c over c, the whole thing squared, so you can cancel the c. And then times the proper length of the Earth, it was 45 kilometers, so 4500. Right, so according to the particle only travels 4.31 kilometers, which was 4310 meters. Okay. Now, this is the interesting thing to show us that the consistency. In the particle's frame, right, how much time does it take to travel from the start to the end? Okay, so calculate this by the time dilation formula and the other formula. So let us find out. Okay, so according to the particle's frame, its time of existence is the proper time, right? Every object measures their own proper time. So its own time of existence is proper time. So we're going to call this delta t0. Okay, so it's going to be the proper time in this frame. So using the length contraction formula, right? So this is the proper time, but the time measured by Earth is not proper. So the time measured by Earth is not proper. So I should write this down to be more clear. The time of measured by Earth is not proper. So the delta t in answer of part A, right, is not the proper time because the particle is moving relative to the Earth. So the value that we got was not a proper time. So this number is not proper time. Okay, so we want to figure out what is this. So see, again, right, we just need to identify who proper time, who is not. Then we put in the formula correctly by the time dilation formula. So from there, from the time dilation, we get delta t0 is dt over gamma. So it's so it's 1 minus u squared over c squared, square root times the time over here. So the relative speed is 0.9954 c over c, the whole thing square, and then the square root, and then the time is 1.507 times 10 to the 4. Okay, then calculating everything, you get the number that shall be our proper time. It turns out to be 1.44 times 10 to the minus 5 seconds. So it's much shorter compared to this time. So the proper time is usually is the smaller time, right? Because your original time is the longest time. Then you measure other people's frame is dilated, so it is drag on longer. Okay, so a short time interval. What I mean is this. Okay, so so we have calculated the answer already, but we can also calculate this in another way. So because what we have here is that we can calculate using the kinematic equation. So what I'm trying to say is distance traveled according to the particle is not the proper length, but we do have a distance value. Is L is 4310 meter. So this is not the proper length. but it is the value measured in the particle frame, right? Let's say particle is Bob. Okay, so the speed relative to the particle, right, so that means speed of Earth relative to the particle is the U is 0.9954 c. So from these two information we can calculate the time taken. So using our normal kinematics formula, delta t is just L over U. So if you divide these two, you will just find the same answer again. So it's consistent. Okay, because time dilation will, the reason why we have time dilation and length contraction is the same reason. So if your time is dilated, then your length is contracted by the same factor, and using one or the other, you can still calculate the result consistently. Okay, any question? Yeah, we ignore the acceleration due to mg, because the part, hang on, there's a lot of other things. Usually right, actually it doesn't matter who is u, who is v, but usually u is the relative velocity between two frames. So there's no difference here. The difference only come in when you talk about three objects, right? So usually what our situation is, we have Alice, right, and then we have Bob. Usually I have two frames, so the speed between two frames is u, okay. But right now the particle itself is Bob, so that's fine, right? So we have only two objects in this problem here, okay. So the Earth and the particle, and only two. That's why only two objects. Some other question is more complicated. Let's say I have a third particle, okay. So the third particle then the velocity of the particle measured by Bob is v prime, velocity measured by Alice is v. So this is where we call this v, okay. But if there's only two objects, then whether it's u or v is it doesn't matter. Actually it doesn't matter here, but usually I tend to write it in this way, right? So if there's a third object, I think question 4 will have 3 objects, so you know what I'm talking about. What's the other stuff? Yeah, but this is another case. Sometimes in the case where I consider small velocity, then but not all the time. So this not always true. So yes, we ignore acceleration due to mg, and the reason is because the velocities here is very high. So the acceleration is 9.8 meters per second square. So actually it does accelerate due to mg, but it will not change the actual velocity. It will change in like the many decimal places at the back, and it will not appear in the front. It will change. It will increase by a little bit, but still very fast. So yes, in other words, we are ignoring the acceleration because g is 9.81, so it's much smaller compared to c. C is like 10 to the power 8. This is like 10. You know. So yeah. Should we even take a break? We're gonna finish early, so we have 4 more questions to do. Shall we just finish off all the things in one shot? I can't decide. 45. 45. 5 more. Let's take a 10 minutes break. I will want to like clear my nose for a bit. So it's just distance over time. Yeah, so delta t is the time interval, so the time interval is the length over the speed, right? Yeah, so it's not a calculus type of delta. Yeah, when the delta here is not the calculus thing. Okay, so let's take a 10 minutes break. If you're fine with it, then I will yeah, let's rest for a while, and then after we come back we will finish the last 4 questions only, and then we will finish. The U is too weak, so we need C to kill the U guy. Did he say something like this? I have not watched his recent videos. Okay, so since we are breaking, I will stop the recording. It's quite user-friendly nowadays. It's quite user-friendly nowadays, and the good thing about Linux is most things are free. If you want to get Photoshop, there is a Linux version, and you can do Photoshop things. If you want Microsoft Word, there's a free version of all kinds of things there. And if you want to do work like programming and things, usually it's more convenient on the Linux. Yeah, so we are at question 4, right? So question 4 is the one case. Yes, it is now we consider 3 objects. So one of them will be Alice, one of them will be Bob, one of them will be the point P. So let's look at this. 2 particles are created in a high energy accelerator and move off in opposite directions. The speed of one particle measured in the lab is 0.65 c, and the speed of each particle relative to the other is 0.95 c. So yeah, so we need to interpret this and identify what are my u, v, and v prime. So we need to identify what is the speed of second particle measured in the laboratory. So it will make sense if we just assign who is Alice, who is Bob, and who is P. Right, so once we assign it, and then everything becomes very simple. So the challenging part is to read the question and understand and decide. It is your decision, because you can decide, you can assign it in another way. But once you decide who is Alice, who is Bob, then the rest should be pretty okay. So we have 3 objects here: the lab, particle 1, and particle 2. So one of them can be Alice. So why not let's make Alice to be the lab. Okay, and then 2 more particles. So one of them shall be Bob. This is particle 1. And then the point P is particle 2. Okay, so according to the question, right, the speed of the particle measured by the lab is 0.61. So speed of one particle, so is the let's take this as my first particle. So the speed of particle 1 measured measured by the lab is u, okay, and so it's 0.650 c. Okay, so because speed of particle 1 measured by the lab, that means it is speed of Bob measured by Alice. So this is the relative motion between s and s prime. So I'm going to call this u. Okay, so this speed of particle 1 measured by Alice is going to be this. So the speed of particle 2, according to the question, right, the question actually says the speed of each particle relative to each other. So so speed of particle 2 relative to particle 1. So we can say speed particle 2 measured by particle 1. Excuse me. So let's call this the speed first. Let's not worry about direction first. So according to the question is 0.950 c. Okay, so this is the relative speed relative to each other. Okay, so what I want to calculate now is, according to the question, we want to find speed of the second particle measured by the lab. So speed of particle 2 measured by the lab. So what is the speed of particle 2 measured by lab? Okay, so that means speed of particle 1 measured by lab is the s prime frame is v prime, so the measured by lab is v without the prime, and we want to calculate this. Okay, so here we are only talking about speed. We only know that these two particles are traveling opposite, right? And then so we shall choose one of the directions to be our x direction. So we shall let particle 1 travel in the positive x direction. So therefore particle 2 is in the negative. Okay, so in other words, my u is a positive number. So Bob is particle 1. So he's traveling forward at positive x. So it's positive 0.650 c. And then particle 2 is in the negative x direction. So particle 2 is coming towards Bob, right? So from the Bob's point of view, particle 2 is coming to him. So it's negative 0.950 c. Okay, then we use the Lorentz transformation formula for v, right? So I want to find v. So the inverse transformation is v prime plus u, right? Remember? So 1 plus u v prime over c squared. So if I put in the inverse transformation numbers, it is negative 0.950 c plus 0.650 c, and then dividing all these numbers. So 1, and then so it is going to be, hang on a second, is it correct? One plus 0.650 c 0.950 c over c squared. So if you calculate everything correctly, it is going to be negative 0.3 c over 0.3825. And then putting everything together, you will get negative 0.784 c. I don't know if I made a mistake. I will check this in detail later, right? But the final answer is the one that's correct, because this is a textbook question. So yeah, so this is the speed measured by Alice. So that was question 4. Yeah, I guess so. Thanks, and yeah, bless me for. I heard the news. So so at the moment, that's all for question 8. Question 4 only one part, right? Yeah. So then next question is question 5. Question 5 is this. Question 5 is two particles on a high energy accelerator approaching each other with a speed of 0.520. So just a slightly different number compared to this. That's why I felt a bit strange, but yeah, similar number. Measured in the laboratory, what is the magnitude of velocity of one particle relative to the other? Okay, so similar method again, right? I have two particles and one laboratory, so I need to choose who is the lab, who is Alice, and who is Bob. Okay, so we shall do this here. Question 5. Okay, so question 5 is like this. We shall choose Alice to be the lab again, and then we choose Bob to be S prime, the particle 1, and then we choose P to be particle 2. Okay, and then one of them is, so again, this is another scenario where they travel in opposite directions. So let us say that this is traveling in the negative x direction, and then this is traveling in the positive direction. Okay, so one is traveling to the left, one is traveling to the right. So according to the info given, the particle 1 the particle, both of the particle is having this speed measured by the laboratory. So both is having the magnitude 0.9520 c, relative to the laboratory. So if I say Bob is traveling in the negative x direction, I must put it this way, right? And then for the other particle is in the same speed but different direction. So we shall say that this is v measured by Alice. So it is going to be 0.9520 c measured by Alice. And then we want to determine what is the magnitude of the velocity of one particle relative to each other. That means one particle relative to the other particle. So what is the velocity of particle 2 relative to Bob? So that what we are looking for is v prime. Okay, so v prime here. Then if I use it this way, using the Lorentz velocity transformation formula, it is v minus u 1 minus uv over c squared. So my v is this number, and then u is this number, divided by 1 minus uv over c squared. So it's negative 0.9520 c over 0.9520 c over c squared. So this c cancel each other. All this can be simplified and calculated, so you get 0.9988 c. Okay, yeah, so that was question 5. Okay, so this is page 4, this is page 5. Yeah, excuse me, I need to clear my nose again. My nose is very bad today. Okay, so we continue with 3 more questions, 6, 7, 8, and then we're done, right? So question 6. Okay, any question? So question 6 is a very simple energy question. A 60 kg person is standing on level ground. How fast does she need to run to double her total energy and then or increase by factor of 10? So yeah, let's calculate this. This is very easy. Just to make us practice the energy question. So remember, right, our total energy formula is given by E is equals to mc square 1 minus v square over c squared. So this is the total energy of a particle traveling at speed v. Right, so if v is 0, the energy is mc squared. So according to the question, initially the person is at rest. So therefore the initial energy, I'm going to call this EI, is just equals to mc squared. Okay, so I want to move at speed v to double initial energy. So this means that my energy when I'm running must be twice of my initial energy. Very simple, right? So my energy is mc squared over 1 minus v squared over c squared. I want to find what is the correct v to make sure that I have 2 times of mc squared. Okay, so cancel this. And then I got 1 minus v squared over c squared is equals to half. So that square root, right? So if I open the square root, it becomes 1 over 4. So that my v squared over c squared becomes 1 minus a quarter. So it's 3 over 4. So v is equals to root 3 over 2 c is going to be 0.8660 c. Correct, right? Yeah, correct. Okay, so this is the speed that you need to double your total energy. What if I want to move at speed v to increase by a factor of 10? So that means my final energy at my moving speed v is 10 times my initial energy. So my mc square is equals to 1 minus v square over c square, the square root. and then 10 times my initial energy. My initial energy is just the rest energy, so 10 mc squared. So cancelling this, then I got 1 minus v squared over c squared. Square root is 1 over 10. So 1 minus v squared over c squared is 1 over 100. V squared over c squared is 99 over 100. Yeah, just simplify. So it's 99 over 100c. So it's 0.994987 c. So this is the speed that you need to run to increase your energy by a factor of 10, right? So again, all this involve like very, very high speed, and special relativity effects only come in when you have very high velocities. Okay. Any other question? So yeah, so question 7 now. So question 7 is a particle having a rest mass and having momentum. So according to the question, the rest mass is given to be, let me copy this down, 6.64 times 10 to the minus 27 kg, and then the momentum P is equal to 2.10 times 10 to the minus 18 kg meters per second. So the question say rest mass, but remember what I said, right? For us, there's only one mass, so every mass is the rest mass as far as I'm concerned, right? So only the momentum is affected by relativity, the Lorentz factor. So what we want to calculate is the total energy of the particle. So we are given m and we are given p, right? So what we can do is we shall use the energy formula. So remember, the energy formula is just mc square plus pc square. So this is the formula for the total energy which I derived at the end of Monday class, right? So we just need to calculate everything together. So 6.64 times 10 to the 27 times the speed of light, and square this, and then the momentum 2.10 times 10 to the 8 times the speed of light, and I square this. So at the end of the day, you're going to get 3.5713 times 10 to the minus 19 minus 3.969 times 10 to the minus 19. So once you add the two numbers up and you take the square root, the final answer is 8.68 times 10 to the minus 10 joules. So the energy is very low. Is it correct? Yeah, these are very low. Okay. Then the next thing that you want to do is kinetic energy and the ratio of the kinetic energy and the rest energy. So kinetic energy is just the total energy subtract mc square, right? So it's this number that you calculated minus mc squared, so 6.64 times 10 to the 27 times speed of light square. So you're going to get this number 2.70 times 10 to the minus 10 joules. Okay, and finally I want to find the ratio between the kinetic energy and the rest energy. So you just divide these two numbers. Mc squared was 6.64 times 10 to the 27 times the speed of light square. So all these are numbers, right? The calculation is pretty boring, but the ratio is about 45%. Okay. So now we are at question 8, and question 8 is the one that will involve some calculation a bit. So show that according to relativistic mechanics, the particle speed under a constant force approaches c at time goes to 0. Okay, so let us show this explicitly, right? So remember, when we're talking about relativity, right, our relativistic force has a formula. Which is given by ma, but it's no longer just ma, because if it's traveling at very high speed, then I need to include this term to the power 3 over 2, right? It is obtained by differentiating the relativistic momentum, and for this case we are talking about a constant force. Okay, So constant force, and then let me solve this equation for the acceleration. So I got F over m 1 minus v squared over c squared to the power 3 over 2. So I want to find what is the velocity as a function of time. Then I can take the limit. So what I can do is I can write my acceleration as dv dt. This is F over m 1 minus v squared over c squared to the power 3 over 2. And then I will integrate both sides of the equation. Okay, so I got hang on, I need to bring this down first. So dv over 1 minus v squared over c squared to the power 3 over 2, and then this is F over m dt. So I want to integrate both sides of the equation. Okay, so let me write a new line next. So let's say I start from rest. Okay, so if I start from rest, my initial speed is 0, and I want to get some final velocity v. So I'm integrating this with respect to v, and then integrate from 0 to some later time, F over m dt. Okay, so how do you integrate this? Why suddenly your mind go boom? We are not doing anything special, right? Hopefully not, but how do you integrate this? This is again a calculus problem, so I will just tell you the answer. The antiderivative is v over 1 minus v squared over c squared square root. So this is the integral of this. Okay, well, at least we can at least check right? So once you've got the answer, we can at least check what happens if I differentiate this function. Okay, so last time I used the product rule, but so right now I think everyone is more comfortable with quotient rule, so let us use the quotient rule here. So I square the bottom, I differentiate the top, and then I times it with this factor, and then minus this one, keep it, and then I differentiate the square root stuff. So if I differentiate the square root stuff, I got 1 over half, right? And then now it's 1 minus v squared over c squared. Differentiate this, it will now becomes to the power of half, right? And then I need to differentiate this 2v over c squared. It looks very messy, so let me clean this up a bit. So if I differentiate this, I will get minus minus cancel. The half and 2 will cancel here. So what I have is plus v over c squared, and then 1 over square root of v squared over c squared. And then I got 1 minus v squared over c squared. Okay, so to simplify this equation, what I can do is I will times top and bottom by this factor. So if I times this already, the downstairs this times this becomes to the power 3 over 2. And then this times this, I got 1 minus v squared over c squared. This times this will cancel the factor plus v squared, v to the power 1 over, hang on, v squared. Yeah, v squared over c squared. Then these two will cancel each other. And at the end of the day, we have proven that the derivative of this is 1 over this. So therefore, my integral, right? So my integral is, my integral now becomes this. So let me copy one more time. On the right hand side is integral from 0 to t f over m dt. So all this stuff here is constant, right? So all this stuff here is constant. So on the right hand side, it just a t comes out. Okay, and then on the left hand side, it becomes the antiderivative. So it becomes this. And then this is just f over mt. Okay, and then you put in the limit. So when you substitute any arbitrary v, so I got v 1 minus v squared over c squared. The lower limit is 0, so I got this, and then I got f over mt, right? And I want to solve this equation for v. So I want to find v as a function of time. So let's square both sides of the equation. So squaring both sides of the equation, I got v squared 1 minus v squared over c squared, f2t2 over m square, right? And then so that my v square is this thing minus f square t square over m square b square over c square. Okay, then I bring this over. So let me check if I made any mistake. I need to bring this over to plus, right? So both terms have a factor of v. So if I bring this over to plus, I got 1 plus f square t square over m square c square. This whole thing is v. Okay, and then we simplify. So we got, let's write it in this way. Okay, so that my v square now is f square t square over m square, and then this is 1 plus f square t square over m square, and then there's an extra c square. So what I'm going to do is I want to simplify this factor out. So I got this will become 1 over m square over f square t square plus 1 over c square. Do you agree? Right? So this is the v. So the speed is taking the square root. So I got 1 over the square root of m square over f square t square plus 1 over c square. Okay, so this is the velocity as a function of time. And then if I increase the if I increase my velocity, right, taking the limit of t going to infinity, then it just becomes 1 over the square root of 0 plus 1 over c square. So you get c. So we have finally proven that the limit of a constant force from rest when time goes on to infinity is just approaching the speed of light. So it doesn't increase forever, right? It will increase asymptotically reaching the speed of light. This is a particle for a constant force. Okay, so yeah, so this is what we got. We are supposed to compare this to the Newtonian calculation. So let's check the Newtonian calculation. Remember Newtonian mechanics, everyone should know how to do it by now, right? So F is equal to ma. There is no speed of light factor here. And if F is constant, then F is equal to ma will just give me a is equal to F over m. Then it's a constant, right? So if it's a constant, so that means acceleration is a constant in Newtonian mechanics. In Newtonian mechanics, when you have acceleration constant, what do? You use your kinematic equation like this, right? And I start from rest, so v is equal to F over mt. So in Newtonian mechanics, if my force is constant, your velocity is increasing linearly in time. This one everyone knows from Newtonian mechanics. But if Newtonian mechanics is true, right? If I have a constant force, if I wait long enough, eventually I can accelerate. If it's increasing linearly forever. So if I wait long enough under a constant force, you expect something to go beyond the speed of light. Okay? Because taking the limit of t to infinity of v is infinity. So it can go any time as fast as you want, faster than the speed of light and beyond. But this is not true, right? This is not true because Newtonian mechanics is not accurate when velocity approaches the speed of light. Okay, so yeah, so that is what I'm trying to say. Okay. So so the reason is this. Okay, so the reason is this. So let's call this equation 1, right? So this is the relativity equation. Okay, so look at equation 1. So equation 1 is true for relativity. All cases for constant force. Right? So my v is 1 over m square over f square t square plus 1 over c square. Okay, so from this right, we find that if my speed of light, if this number is smaller compared, if this number is larger compared to this number, that means if c is much greater than ft over m, then my v is approximately, if this number is larger than 1 over c square, right, that means for anything that is small compared to the speed of light, then 1 over the speed of light is small, so this term will be negligible. Okay, so if this term is negligible, then this is approximately 1 over m square over f square t square root. So this will give you back the f over mt, which is the same as what we got over here. Okay, so this is true as long as my velocities is small compared to the speed of light. Yeah, ft over m is much smaller than c. Then no longer true when ft over m is approximately this size. So the Newtonian mechanics is true for velocities very small compared to the speed of light. That is why we can use this equation. But the lesson that we learned from special relativity, right, this equation is actually wrong, because the correct equation is like this. So why is it our results are still okay by using this equation is because this term is more bigger compared to this. So these two equations are similar when my velocity is close to the speed of light. So they are similar, right? But the Newtonian equation is actually wrong. And the relativity equation, if you include the fact of, you know, special relativity postulates 1 and 2, then this our equation, this equation is no longer correct. So we must use the correct equation to describe this. So this is why people say when Einstein discovered relativity, he replaced Newton, because Newton equation is turns out is actually not true. It's only true as an approximation, and the equation that was derived by Einstein is true for any velocity, any case. And that is why we say that, yeah, the special relativity, actually the correct theory, Newton's theory is only the approximation. So yeah, so that concludes our tutorial 10, our final tutorial. So that was the last thing to cover here. Oh, okay. M is not fixed. M is fixed. So that's why I say M here refers to the rest mass, not the relativistic mass. So if for the same particle under a constant force, you will experience this velocity. Correct. That is, yeah. No. That's why I said on Monday, mass is mass. Then the Incredibles meme applies to me. Mass is just mass. So we are talking about rest mass. So we do not use the this is not the relativistic mass. It's just the rest mass all the way. Okay. So m is a value. So if you're given the mass of a particle, then we use that mass. Yeah. So like in the earlier question, right? You're given a mass. That is always gonna be this m. For example, if this is the mass, then we always use this number throughout the whole process. And we always use rest mass here. And also, like for more fundamental reasons, mass is actually kind of like the speed of light. It is a fundamental quantity that is independent of frames. So in more advanced courses, you learn about things that are scale invariants. So Lorentz invariant quantities are the speed of light and mass. Mass is a Lorentz invariant. So yeah, so that is why I disagree with the year 1 textbooks. Usually both these textbooks are taught for year 1 level, right? But this concept will no longer be used after that, year 2, year 3 onwards. So mass is a conserved quantity, right? Energy is a conserved quantity. If your equations are time symmetric, you have conservation of momentum, conservation of angular momentum, all those things, right? Okay, so that's it for today. Does anyone have any question? Yeah, so we are ending early. It's only 4:30, but we finished everything already. Okay, so the rest is for you guys to study for exam, I guess. Then Correct. So momentum, there's a relativistic momentum. Yes. So momentum will be affected by the gamma factor, because we have the for the is mv 1 minus v squared over c squared. Yeah. So this is the yeah, and the reason why people say relativistic mass is some people will define this as the relativistic mass. But it's just a definition. Is the mass, relativistic mass, is defined to be velocity dependent. But this is just mass, right? It's not a real mass. The fundamental, the true and rest, the actual mass is this. So mass, the actual mass, this term is a constant, right? The mass of the proton, mass of the electron, you have some value, so it's always this value. Okay, and this is the actual mass. So that's why I don't like, you can define it in this way, you call this mr or m relativistic, but it's just a mass divided by something, right? It doesn't really have a proper physical meaning. So this one has a physical meaning. That means it's something that can be measured by experiment. This one, you can say, well, you can measure m by experiment and you measure the velocity, so you can measure the ratio, but it doesn't feel like it's very important, right? If you actually look at it. So yeah, so it's not the mass but momentum, and only the momentum and the force is affected by it. And why is momentum given by this? It's also like everything is very consistent actually. So in the future you will learn Lagrangian mechanics. We will have the correct definition of momentum. So our definition of momentum, right, whether it's this or this, is again also an approximate one, or it's only for specific cases, right? And the actual definition of momentum, you will need some higher level physics to learn this, but the actual level of momentum actually is just one definition. And from there, all the concept of linear momentum comes out, angular momentum also comes out, and natural by the same definition. So that is why, and that definition is by using the same method for relativistic case, this comes out. So so that is another thing that is fundamental as well. Yeah. Okay. So we are ending early. That's all for today, I guess. We can measure V, yes. It's hard to answer this question now. Yeah, generally it's true that M is harder to measure, yes. So M is harder to measure, but by the equation E equals to mc square, right? Everything is actually hard to measure. It's not to say that something hard or easy, I shouldn't use that word. It's to say that something has a more fundamental quantity. So energy is conserved, right? So that is a truth that is a law of physics, right? It's true in every situation, and there's a conservation of energy. And because E is equal to mc square, right? If my energy is conserved, speed of light is always c, so m is also always conserved. Okay, so the total energy of the system is, we did not discuss this in detail, but the total energy of the system is kind of like, is it independent? Is a Lorentz invariant? It should be. So what I'm trying to, yeah, so at least for the moment, right, for this year, the reason is because energy is conserved, so mass is conserved, and energy will not be affected by the velocity. For this situation, the definition momentum is not really math yet. Is the physics concept, is the physics that you haven't learned yet. You learn this in year 2. Yeah, is the Lagrangian Hamiltonian mechanics. So it's very hard. Yeah, that's why it's a bit hard to discuss this concept now because we need the Lagrangian concept. If you're interested, you can read the Wikipedia or you can Google or something. So, but it's very important. So Hamiltonian. Save it for year 2. Okay, yeah, good. Then, yeah. I guess when you're older, you're less scared by things as well. The twin paradox. Yeah, so the twin paradox is about who is the older one, right? Because according to the twin paradox is actually, right, to understand why it's a paradox, we need to understand time dilation, right? If you read the paradox and then you think that actually there's a few levels. So for someone who is not familiar with special relativity or just like understanding it imperfectly, right, does not have a correct understanding of relativity, only understand partially, then you will think that paradox is not a paradox. It's like, okay, it's correct. Then when you understand time dilation correctly, then you realize, okay, something is wrong. But then you understand even further, then actually, yes, the answer makes sense. So it's not actually a paradox, correct? Yes. So the twin paradox is a paradox that actually has a solution. Yeah. So the idea is this, okay? Because, right, yeah, so Alice has a watch. And then Bob has a watch. Okay. So let's say so Alice has a watch, and then Bob has a watch. So because of time dilation, right, Alice observes Bob's watch to run slower due to time dilation, because this is time dilation. Slower, so your delta t is equals to gamma delta t proper. Okay, so this is the proper time of Bob's watch. Okay, so now I'm calling t to be the variable on the Bob's watch. So I need a second because Alice's watch is a second watch. So let me call this tau. Okay, so then Bob's. So tau, the watch tau is a proper time in Alice. So Bob observes Alice's watch to run slower. So my delta tau is equals to gamma tau 0, right? So two person always say the opposite things, right? Alice say Bob is slow, then Bob say Alice is slow. So who is correct, right? It cannot be both true at the same time, right? Because if someone is slow, then someone will be older by the time they come back together, correct? Yeah, because it's the naming it's a paradox but has a solution. It has a paradox, because some paradox have solution, some paradox have no solution. Yes, that's why. Yeah. So once we know the answer, but we still refer to the question as a question, right? So some question has an answer already, but we still refer to the title as a twin paradox. It's just a name. So this is the twin so this is the time dilation situation. So where does the paradox come in? Okay, so let's say Bob is on the spaceship. At the time I was calling him Buzz and Alice is Woody, right? So if Bob goes on a spaceship, okay, by the way, Alice and Bob are the same age. Initially same age. Okay, so if Alice goes on a spaceship, okay, and travels at some speed u, and then comes back, then who is correct, who is older? Because when you come back, right, you can stand side by side, right? So you can stand side by side. So one person will definitely be the older person, the other person will definitely be the younger person, right? Because the time dilation, right? They cannot be the same age, because then that means there's no time dilation for each other. So one of them must be wrong. So that is the paradox here. Yeah. So the answer is, right, so what is happening here is that Alice is on Earth, and then Bob goes on a spaceship. Okay. So the reason why is that initially, if you're talking about special relativity, right? So if you're talking about special relativity, all frames are equivalent. So all inertial frames are equivalent. Okay, so that is another thing that I should have emphasized more when we talk about inertial frames. So inertial frames are equivalent. That means we do not say who is correct, who is wrong. Actually, nobody is correct, nobody is wrong, because everybody has their own measurement. That is why, relativity, right? But sometimes you can actually compare and get the outcome. So one of them has to be wrong. Okay, so the wrong one should be the and the reason why one of them is wrong is because this part is no longer inertial. Okay, so if it's not inertial, then both frames no longer equivalent. So that is why. Yeah, am I making any sense? Right, so Alice is inertial all the time because she does not experience any acceleration. The reason why Bob is having an inertial frame is because an acceleration is a force that you can definitely feel. So at this point, right, he feels a force here. So there is some external force in this situation. For Alice, there is no external force throughout the entire process. So Alice is always an inertial frame all the time. So there is something changing happening here already. So both frames are no longer equivalent. And actually, if you use the space-time diagram to draw, right, you can actually determine the difference in the aging time. So, but that's the part I skipped. Okay. Yes and yeah. So the old correct. So the fast is, yeah. So what I meant is here lah. Not to say the faster frame, but we haven't actually calculated why Bob is younger, right? But the frame that experiences acceleration will be younger as well. So there's some additional dilation because of acceleration. And if you learn relativity, you will learn it as the gravitational time dilation. So that is why Bob becomes younger. And is judging by the acceleration. The reason why I say judging by acceleration is to identify something that is no longer inertial frame anymore. So if it's something no longer inertial frame anymore, then one of the calculation must be wrong. Yeah. Because why not to say wrong? One of the calculation must be because when you do this, right, we are using special relativity. Special relativity is assuming everything is inertial frame. Relative velocity is constant. Yeah. Lorentz transformation is also for inertial frames. Yeah, so if you use the Lorentz transformation, right, like the what was the formula? Yeah, so it's v plus u v prime 1 plus v prime u over c square. When we use this inertial frame, well, the u is constant. if it's changing over the motion also, then it's no longer inertial frame. So Lorentz transformation is also for inertial frame only, and this whole chapter actually is all assuming inertial frames when we use the coordinate system. Yeah, okay. So yeah, does anyone have any other question? Yeah, so we finished already, right? Mind blown. Yeah, so this is what happens in special relativity, right? But if you think about it, right, it's a bit contradictory, because special relativity is the format that is consistent, right? And our minds are blown is because when we use Newtonian mechanics, we do not notice the inconsistency, right? Because if we assume absolute time, then the speed of light is things like that, and yeah, so it's not what is actually true. So if we actually calculate everything consistently, that is how we get all the Lorentz transformation and things like that. Yeah. So like any student now, right, if you go back to Newton's age, then you will be a big deal, because you know all the knowledge that people didn't know yet. So that is why, that is the challenge of research, right? Discovering knowledge for the first time is very hard, but once you discover already, then it becomes easy after that, right? So and that is actually common, and what you guys are going through right now, right? Because you guys are saying calculus is difficult, linear algebra is difficult, special relativity, your mind is blown. It's because you are learning it for the first time. Then after you learn it already, right, then the next course, it becomes like normal already, then it becomes easy. So if you transfer this backwards, if you take Newtonian mechanics, which is normal to us now, right? Every one of you guys know Newtonian mechanics, but if you go back to Newton's time, you will blow everybody's mind. And the thing that blows people's mind back then, right, is the acceleration of gravity is constant for every mass. Yeah, it's something not obvious to them at the time, because people think, okay, stone drop very fast, then a piece of paper fall down very slowly, right? And then you go back and tell them every object accelerates at 9.8 meters per second square, you will blow their minds. So it's kind of everything is the same. Everything is different. You mean, yeah, like what I'm saying now, right? For you guys, calculus, linear algebra. Yeah, like you go back to Newton's time and then you show them your smartphone, show them your iPhone, you show them your camera phone videos and things like that. Yeah, actually, yeah, for everyone else, if you want to log out, you can log out already. That's all I wanted to say for today. So that is the final lecture. Then I'll just stay to answer questions. That is also true. Right? So if you go back and then they will call you to be the witch. Yeah, ether. It's called ether. Correct. Yeah, ether. Actually, ether is coming back now. So there's something called Einstein ether theory. That we bring back the concept of ether again. Yeah, so I got a few papers. Yeah, actually, it's called Einstein ether theory. So, I don't want to show you equation, it will just scare you. But the idea of ether, the possibility of ether is coming back. It's not Einstein's paper, because Einstein removed ether from the concept, right? But now we are combining Einstein, and then there is some ether, but it's still Lorentz invariant. No, actually no. It's not Lorentz invariant, but it's somehow is consistent with special relativity, and it is made to explain the dark matter problem and the dark energy problem. So it's still a theory. It's not proven yet. I think it's not true. Actually, it's probably not true. It's one of the theory, but it hasn't been worked out yet. Actually, I should stop recording.